Hello everyone, welcome to my class. In today's class I am going to cover inverse trigonometric functions. So let me start the class right away. First, quick recall about inverse functions. If a function f is 1 to 1, then it has an inverse. We denote the inverse by f raised to the power negative 1. The inverse functions f inverse is a function that undoes the action of the original function f. So for 1-to-1 functions f, if y equals to f of x, then f inverse y equals to x. So let me talk about this diagram here. Here is our functions f going from the domain here, which carries x and gives us y equals to f of x, and also f is 1 to 1. Then we can define an inverse of f going from this set to this set. So that means domain of f is the range of f inverse, and range of f is the domain of f inverse. And the fact, the graph of the inverse function is a reflection of the graph of original functions across the line, the diagonal line y equals to x. Now quick side note, trigonometric functions are not one-to-one functions and their domain of definitions. However, we can create one-to-one trigonometric functions by restricting their domains and define the inverses of those restricted trigonometric functions. Side note 2, domains of trig functions are measure of angles, whereas the ranges are the ratios. For any real numbers t, the coordinate of a point, the coordinate are x and y, on the unit circle corresponds to the angle t are the outputs of the trig functions. So we have x equals to cosine t and y equals to sine of t. Notations for inverse trigonometric functions. Inverse sine function is denoted by sine inverse x or arcsin x. Similarly, inverse cosine function is denoted by cosine inverse x or arccosine x. Similarly, inverse tangent function is denoted by tan inverse x or arctan x. Inverse secant function is denoted by secant inverse x or arcsecant x. Inverse cosecant function is denoted by cosecant inverse x or arccosecant x. Inverse cotangent function is denoted by cotangent inverse x, that's a cot inverse x, or arccot x. Alert, sine inverse x is not equals to 1 over sine x. Similarly, cosine inverse x is not equals to 1 over cosine x. Tangent inverse x is not equals to 1 over tan x, etc. Now, next, the inverse sine functions. For restricted sine functions in the domain negative pi half to pi half, the inverse function is defined as y equals to sine inverse x if and only if, this two arrow means left hand side implies right hand side and right hand side implies left hand side. So these are the equivalent expressions. Y equals to sine inverse x if and only if x equals to sine y. The inverse sine functions has domain negative 1 to 1 and range negative pi half to pi half. So now let me visualize. So here, that's better. First graph. This is the graph of y equals to sine x. So the sine graph we are familiar. It just goes wrapping around the x-axis, same as to the left side. But I truncated the domain from negative pi half to positive pi half. So I'm only talking about this piece because this piece is 1 to 1. Because any horizontal line crosses the graph only at one point. So this piece of the sine function is 1 to 1. Then we can define its inverse. The inverse is then this one. So by the way, again in the first diagram, the domain of this sine functions, that means I'm talking the restricted sine function, domain is minus pi half to pi half, and the range is minus 1 to plus 1. So for the inverse functions, domain is negative 1 to positive 1, and range is minus pi half to positive pi half, and the graph of sine inverse x is simply the reflection of this sine x graph across the line y equals to x. Across the line y equals to x. So the graph of sine inverse x is this one. Let me combine these two graphs, sine graph and sine inverse graph, in the third diagram here. Let me scroll down. Then the graph looks like here. This is the sine graph, and we are only talking this piece, the sine graph truncated at pi half to negative pi half, so this piece, and its inverse is this graph, and the inverse is the reflection of the sine graph truncated in minus pi half to plus pi half. I hope this makes sense to you all. Now let's move on. Inverse sine functions property. For fx equals to sine x and f inverse x equals to sine inverse x, the following hold true. F composite f inverse at x equals to f of f inverse at x equals to sine of sine inverse x. Then the function and inverse function cancel, so only gives us x for all x in the domain of f inverse. Similarly, I can switch these compositions. F inverse compositions with f evaluate at x equals to f inverse of fx equals to sine inverse of sine x equals to x for all x in the domain of f. Great. Similarly, let's talk about inverse cosine functions. For restricted cosine functions in the domain 0 to pi, the inverse cosine function is defined as y equals to cosine inverse x if and only if x equals to cosine y. So here y equals to cosine inverse x, then you multiply both sides by cosine functions, then the left side is cosine y, right side is simply x, because function and inverse cancel out, and I wrote right side to left side here. I hope this makes sense to you all. The inverse cosine functions has domain negative 1 to 1 and range is 0 to pi. Let me show you the graph here. So here we are familiar of the cosine functions graph. So this is the cosine functions graph, and we are truncating the domain of cosine functions here from 0 to pi. So I'm only talking about this piece only, the cosine functions here, whose domain is 0 to pi and range is minus 1 to positive 1. Then we are reflecting this graph across the line y equals to x, the diagonal line, and the inverse functions graph looks like this one here. This is the inverse cosine x graph. So the domain of inverse cosine graph is here, from here, minus 1 to positive 1, and the range is from here to here, 0 to pi. I hope this makes sense to you all. Now let's move on. Next, let's talk about inverse cosine functions properties. For f of x equals to cosine x and f inverse of x equals to cosine inverse x, the following hold true. The compositions, f compositions with f inverse, evaluate at x, this equals to cosine of cosine inverse x equals to, again, cosine and cosine inverse cancels, it only gives us x for all x in the domain of f inverse. Similarly, we can switch the position of the function and the inverse. So f inverse compositions of f at x equals to cosine inverse of cosine x equals to x for all x in the domain of f. Great. Next, let's talk about inverse tangent functions. And keep in mind the tangent function has vertical asymptote at pi half and negative pi half. So I'm only truncating my domain at minus pi half to pi half. So for the restricted tangent functions in between negative pi half to pi half, I'm excluding the endpoint here. That's why I use the parenthesis. The inverse tangent functions is defined as y equals to tan inverse x if and only if x equals to tan y. The inverse tangent functions has a domain, everything, negative infinity to positive infinity, and the range is negative pi half to pi half, excluding those endpoints. So let me show you the graph here. So these are the tangent functions graph. We have the vertical asymptote at negative pi half, at positive pi half, and here. But I'm only talking this piece, the tangent functions, this graph in between minus pi half to positive pi half. So here the domain is minus pi half to positive pi half, and range is all real numbers. And now we are flipping this tangent functions graph across the line y equals to x. Then this becomes this graph now. Now this is the inverse tangent functions graph whose domain here are everything, and range is minus pi half to positive pi half. At y equals to pi half and y equals to minus pi half are the horizontal asymptote for the inverse tangent functions here. I hope this makes sense to you all. Now let's move on. Next, let's talk about inverse tangent functions properties. For fx equals to tangent x and f inverse x equals to tangent inverse x, the following hold true. The compositions with f inverse at x equals to tan of tan inverse x equals to x for all x in the domain of f inverse, and we can switch the position of the function and its inverse. Then f inverse compositions f at x equals to tan inverse tan x equals to x for all x in the domain of f. Great. Now let me summarize. Summary chart, composition of a trigonometric function and its inverse. So we just discussed in earlier about those. So now let me talk about here the note. The angle of inverse of sine, cosine and tangent function lies only in their respective range. So the inverse sine functions range is minus pi half to pi half. So that means from first quadrant and fourth quadrant. The range of cosine inverse functions is 0 to pi. That's from first quadrant and second quadrant. Inverse tangent functions range is minus pi half to pi half. That's again fourth quadrant and first quadrant. So the idea here, to solve the compositions sine inverse of sine x, if this x lies in the range of inverse sine functions, then this composition sine inverse sine x gives us x. Else we need to find another angle x star in the range of sine inverse functions such that sine x star equals to sine x, then sine inverse sine x, this composition turns out to be x star, that the angle in the range of sine inverse x. For example, sine inverse of sine 150 degree equals to 30 degree because 30 degree lies in the range of inverse sine functions, which is negative pi half to pi half. 150 degree lies outside this range. I hope this makes sense to you all. Let's move on. So again here, on this unit circle, the sine inverse range is minus pi half to pi half. That means from here, fourth quadrant to first quadrant. Range of cosine inverse x is 0 to pi, means first quadrant and second quadrant. And the inverse tangent function's range is minus pi half to pi half, but excluding those endpoints. So still I'm in fourth quadrant and first quadrant, excluding negative pi half and pi half. So quick example here. What's the value of sine inverse 0? That means sine 0 is 0, right? So here in the unit circle, the y value corresponds to the sine functions and x value corresponds to the cosine functions. So this 0 is the sine 0. So then sine inverse 0 gives us 0. That is the angle 0. Similarly, sine inverse 1 over radical 2. Sine inverse 1 over radical 2. So this one here. So this corresponds to 45 degree. So then sine inverse 1 over radical 2 is 45 degree or pi fourth. Similarly, cosine inverse minus 1. So here, I'm talking about this value now. Cosine inverse minus 1 is then pi, and then pi lies in the range of cosine inverse functions. Similarly, cosine inverse is 0. Cosine inverse 0 is pi half. Great. I hope it makes sense to you all. So maybe one small comment here. Sine inverse 1 over radical 2. It has two choices. One is pi over 4. Another, that means 45 degree. Another is 135 degree. And 135 degree lies in second quadrant. But the range of sine inverse function is minus pi half to pi half. That means that 135 degree is outside this range. So we disregard that choice. So we have only one choice, which is pi fourth. I hope this idea makes sense to you all. That's what I talked here. That's what I talked here. That's what I talked here. Great. Now let's move on. Now similarly, inverse functions for secant functions, cosecant functions, and cotangent functions. We evaluate them by noting the relationship to inverse cosine for secant, inverse sine for cosecant, inverse tangent for cotangent. So we define with this idea. For example, y equals to secant inverse x. Multiply both sides by secant x. This gives us secant y equals to x. This is the equivalent expressions. Again, if you want to leave, let's take its reciprocal. Secant y is 1 over cosine y. Then you flip it. Then cosine y equals to 1 over x. I have this idea makes sense to you all here. Then y equals to cosine inverse 1 over x. To define the secant inverse x with the help of cosine inverse functions. That is, secant inverse x equals to cosine inverse 1 over x for x greater than or equals to 1. For example, secant inverse 2 over radical 3. It turns out that this equals to cosine inverse, you just flip it, radical 3 over 2. And we know cosine inverse radical 3 over 2 is simply pi over 6. Great. Similarly, for cosecant inverse x, similarly cotangent inverse x. And by the way, for cotangent inverse x, equivalently easy to work with this identity here. Cotangent inverse x equals to pi half minus tan inverse x. And by the way, the domain of tan inverse and cotangent inverse is all real lines. Great. Quick remark. For special input values, the output of the inverse trig functions are the special angles. Oh, it's a typo, not triangle. Angles. Let me hide this part. Yeah. Special angles. Drawing a reference right triangle helps in determining the ratios when evaluating the mixed trig compositions. applications. One practical applications of inverse trig functions involves in determining the angle of elevations and angle of depression, also for integrating rational functions. Great. Now with those ideas, now let's do some example. Example 1. Evaluate the following inverse trig functions from part A through F. Part A, evaluate sine of sine inverse radical 2 over 2. So here, since radical 2 over 2 lies in this range, -1 to 1, so by the property sine and sine inverse cancels, so then this equals to simply radical 2 over 2. That's the final answer. So let me show you what properties I used here. Sine of sine inverse x equals to x for x lies in these intervals -1 to 1. I hope this makes sense to you all. Let me scroll down. That's better. Next, part B. Evaluate sine inverse sine 150 degree. Since 150 degree does not lie in these intervals, so then we need to find out an angle which angle lies in these intervals, -π½ to π½ such that sine of that angle equals to sine of 150 degree. So then that particular angle is 30 degree, because 30 degree lies in this range -π½ to π½ from -π½ to π½ and also sine 30 degree equals to sine 150 degree. I hope this makes sense to you all. Next, C. Find the value of cosine inverse of minus radical 3 over 2. Solutions. Let y equals to cosine inverse of negative radical 3 over 2. Then we can multiply both sides by cosine function. Then this becomes cosine y equals to simply negative radical 3 over 2. Negative radical 3 over 2. Then we know the range of cosine inverse function is 0 to pi, and 150 degree. At 150 degree, cosine gives us minus radical 3 over 2. So then y equals to 150 degree, and this 150 degree lies in the range of cosine inverse functions. So range of cosine inverse function is 0 to pi. Then our answer is y equals to 150 degree. I hope this idea makes sense to you all. Let me show you again the inverse of cosine functions range, 0 to pi. Great. Let me scroll down. Similarly, part D, let's find the value of tan inverse negative radical 3 over 3. So solutions, let y equals to tan inverse of negative radical 3 over 3. Then this is same as saying tan y equals to minus radical 3 over 3. Then we know at 30 degree, tan 30 equals to radical 3 over 3. And since tangent function is odd function, so this minus is as it is there, and y equals to minus 30 degree. And by the way, the range of inverse tangent function is minus π½ to π². So then minus 30 degree lies in minus π½ to π². So the answer is y equals to then minus 30 degree. Great. So on this chart again, minus 30 degree is here, and we know the range of tan inverse x is minus π½ to π², excluding those π². So our minus 30 degree is the correct answer. Great. Next, part E. Find the value of sine inverse cosecant π4. Solution. This is not defined, as cosecant π4 is radical 2, and radical 2 is 1 point something. which does not lie in this intervals of -1 and 1. Part F, find cosecant of sine inverse radical 2/2. Since sine inverse radical 2/2 is simply pi/4, so cosecant pi/4 is radical 2. Great. I hope it makes sense to you all. Next, let's do example 2. Simplify the mixed composition of inverse trig functions sine inverse of cosine 2 pi/3. Begin the solutions. Write down the trig functions here. Sine inverse of cosine 2 pi/3. Let's find the value of the inside function first. Cosine 2 pi/3 is -1/2, and sine inverse -1/2 is, in the next step, pull this minus outside, then sine inverse 1/2. So minus, this minus is here, and sine inverse 1/2 is pi/6. Great. I hope this idea makes sense to you all. Now let's move on. Example 3. Example 3. Evaluate the composition of inverse trig functions by drawing a right triangle and leveling it. Part A. Cosine of sine inverse -11/61. Begin the solutions. So let's assume this inside functions equals to theta. So let theta equals to sine inverse of -11/61. Then simplify, multiply both sides by sine functions. Then this is equivalent to sine theta equals to -11/61. And we know in right triangle, the sine function is the ratio of perpendicular over hypotenuse. So then P turns out to be -11, hypotenuse turns out to be 61. Then using Pythagorean identity, we can easily find the value of base of that right triangle. So here P equals to radical h square minus p square. Put h equals to 61, p equals to -11, and simplify. It turns out that base is 60. So on the diagram here, let us go down. So this is the hypotenuse. This is the hypotenuse 61. This is the perpendicular -11, and this is the base 60 we just found. Right angle is here, and this is the angle of reference. Then let's use this triangle to answer these questions here. So the given question is cosine of sine inverse -11/61. We assume this inside function equals to theta, so this is simply cosine theta. And this triangle, cosine theta, is the ratio of base over hypotenuse. Here base is 60, hypotenuse is 61. So our answer is, for cosine theta, 60/61. That means the value of this given compositions is 60/61. I hope this idea makes sense to you all. Part B. Find the value of sine of cosine inverse x over radical 16 plus x square. As before, let's assume theta equals to this inside functions here, cosine inverse of x over radical 16 plus x square. Then multiply both sides by cosine function. Then this turns out that cosine theta equals to x over under the radical 16 plus x square. And we know in this right triangle, the cosine function is the ratio of base over hypotenuse. So here b over h. So in this right triangle, this is perpendicular, this is base, this is hypotenuse. So we found b is x, hypotenuse is radical 16 plus x square. Then using Pythagorean identity, we found the perpendicular p equals to under the radical h square minus b square. H is this number, b is this number, and simplify, it turns out that perpendicular is 4. Let me school this way better. Yeah, 4. Then finally, now we are able to label these right triangles and can find the value of this given composition. So given composition equals to, since inside function is theta, we assume, let me scroll this way, then sine theta, and this right triangle is the ratio of perpendicular over hypotenuse. So here p over h, p we found 4, h is already we have here under the radical 16 plus x square. So then our final answer is for these compositions, turns out that 4 over under the radical 16 plus x square. Great. So I hope it makes sense to you all. Now we finish these sections. Thank you.